Part 3, this is for questions 21 to 30. Question 21. In reaction 1, concentrated sulfuric acid is added to potassium chloride and the fumes produced are bubbled into aqueous potassium iodide solution. Now here, if we get potassium chloride, just like sodium chloride, okay, then plus sulfuric acid, here we get hydrogen chloride, then plus potassium hydrogen sulfate. Okay, this is an acid-base reaction because the acid here denotes a proton, so there is one loss of a proton in here. Okay, now that is that. Then the HCl here is expected to react with what? Potassium iodide. Potassium iodide. Here we get no reaction. We know there is what we call the displacement reaction, since chlorine is much more reactive compared to iodine, but the reaction that is going to take place is when chlorine as a molecule then reacts with what? Potassium iodide. For this case, chlorine is going to oxidize this one here, the iodide ions, to iodine, and then for it becomes what? Negatively charged here. So for it becomes reduced and iodine becomes oxidized. So that is what we get here. You see? So that is that. What else? I think we can get potassium. Instead of the chloride, I can have potassium chloride. Now aqueous in there, because here you're using aqueous like that. So that is what you're going to have. So for this case, no reaction. Okay. The brown solution they are putting here would have been because of the oxidation of iodide ions to iodine, but this one doesn't occur when we are using the HCl here. Okay, the reaction will be there if we are using chlorine as a molecule. You see that? So that is where the trick was. So that means I can put off this and this, and I look at these two. Now observation 2, they are saying in reaction 2, potassium chloride is dissolved in aqueous ammonia. We know that chlorine actually dissolves in what? Ammonia. And this is then added to aqueous silver nitrate. Now, what somebody will think about is they will say that since we have introduced silver nitrate is a soluble salt. So we are going to have silver ions in there, then they react with the chloride ions in there, then we shall get a white precipitate. Okay, but remember this one was done in presence of what? Ammonia. You see that? So the chloride in here dissolves in ammonia. Even when you introduce silver nitrate, so long as ammonia is still there, okay, the chloride ions are going to dissolve. So maybe you could get a white PPT at first when silver reacts with the what? And by the way, this one is not supposed to be aqueous. It has to be a solid. But again, in ammonia, that silver chloride, that white precipitate, is again going to dissolve. So giving us a colorless solution, okay? Not a white what? Precipitate. So that's why our answer is what? C. Let me show you in the book. So when we come to this book here in group 17, there is a table here that shows the, you see what I talked about here, about the displacement reaction. Okay, a more reactive halogen can displace a less reactive halogen from a halide solution of a less reactive halogen. So if you look at what we are having here, chlorine as a molecule, So it can displace the bromine here. The bromide ions will be oxidized to the bromine here. You see? Just like also in what? Just like bromine can oxidize the iodide ions to iodine. You see? Like that. But we are having molecules here. We don't have the HCl that we had. You see that? Now, let me take you to what I want you to see here. Yes, here. The chloride ions, yes, you have formed, let's say, the silver ions. The color of the silver halide is a white precipitate. You see? So that's why they put it as one of the answers here, white precipitate. But when you check here, in ammonia, it dissolves, so giving us a colorless solution. Even in concentrated ammonia, it dissolves. You see that? Question 22. The table refers to the hydrogen halides. Which row is correct? Easier to oxidize down the group. Hydrogen halides. Actually, their bond energies decrease down the group. Okay, so it is easier to break them. So thermostability actually decreases down the group. So that means I have to look here, decreases down the group and easier to oxidize down the group. You see? So that is what we are going to have here as a first of all, easier to oxidize down the group. Okay, so thermostability increases down the group, that will be off. More difficult to oxidize, this one has to be off and this one off. So where do we see the two ticks? Here on C. So that means our answer is what? C. But let me show you. When we check the bond energies of these hydrogen halides, okay, the bond energies here, you can see that they keep on decreasing. Okay, so because they keep on decreasing, then it becomes very easy to break those bonds. So they are saying here something that, as you can see in this table, the bond energies decrease going down group 17, making it easier to break the hydrogen-halogen bond. This is because the iodine atom is the largest atom, so the overlap of its outer shell with the hydrogen atom gives a much longer bond length than with the other smaller hydrogen atoms. So the longer the bond, the weaker it is, and the less energy required to break it. Hence, hydrogen iodide is the less thermally stable than the hydrogen fluoride. Another thing that you can look at, hydrogen here is a smaller one. Now this overlap here between this big iodine here, okay? Now the distance is longer between these electrons here and the nuclei, okay? So because the distance is too long, that means we are going to have weaker attraction between the nucleus and these covalently bonded electrons, or these electrons in the covalent bond. So you're going to have a weaker bond. Longer bond, weaker bond. You see that? So that is why thermostability of these halides decreases down the group, okay? And it is easier to oxidize. What does it mean? When they break down, you have, let's say, hydrogen iodide. This one can break down to iodine and then hydrogen. I can put here too. What's the oxidation state of iodine? Oh, in here is -1. Hydrogen, of course, is 0. Then, +1. Then here, iodine, it is going to be 0. So from -1 to 0, that is oxidation. There is increase in the oxidation state. You see that? And of course, hydrogen here is also 0. Then this is reduction. So it's a redox reaction. Question 23. 7.5 grams of nitrogen monoxide reacts with 7.0 grams of carbon monoxide on the surface of the catalytic converter in the exhaust system of the car. what is the total volume of the product gases measured at room conditions. Now, we need to know the reaction. So we have nitrogen monoxide as a gas, then it reacts with carbon monoxide as a gas to give us two gases. One is nitrogen as a gas, and the other one is carbon dioxide. This one helps to curb the problem of acid rain pollution into the air, because when we get nitrogen oxides and they are released in the air, so what is going to happen is that there is going to be the catalytic oxidation of sulfur dioxide. Remember, sulfur is an impurity in these fossil fuels. So when they burn these fossil fuels, there is going to be production of sulfur dioxide. Now it will react with the nitrogen dioxide. Okay, we call it catalytic oxidation because we are going to get sulfur trioxide, then plus the nitrogen monoxide. You see that? Then in the air, of course, nitrogen monoxide will find more oxygen there. It reacts with it, and then you form more nitrogen dioxide. So the process continues. But when this sulfur trioxide reacts with water, then you will get the sulfuric acid, which we call the acid rain. You see that? So a catalytic converter therefore helps us to curb the production of nitrogen oxides because they are the ones that start. Okay, this nitrogen here, nitrogen can react with oxygen, but the activation energy is so high because nitrogen has a big one, has a stronger triple bond, and it is non-polar. Because there are some questions where they ask, explain why nitrogen is unreactive. Okay, it has a strong triple bond and it is non-polar. So let's come back to this one. Let us now balance the equation. So these are two nitrogens. I'll put a 2 here. Then I'll also put a 2 here such that oxygen becomes a 2, and then a 2, making it a 4. So when I put a 2 here, oxygen becomes a 4, and carbon is also 2, as it is here. Now, using these moles here, I'm going to take on the masses, okay? Nitrogen monoxide, we have, this is 2, then times, nitrogen is 14, oxygen is 16. This is 2 times, this will be 12, then plus 16. This is 2 times 14. This is 2 times 12 plus 2 times again 16. So here we are getting 30. So 30 times 2. So based on this reaction here, 60 grams of nitrogen monoxide react with, okay, they react with, this is 28 times 2, react with 56 grams, right? To produce 28 grams of nitrogen as a gas, and then also 88 grams of carbon dioxide. You see that? Then they said now 7.5 grams of nitrogen monoxide. So 7.5. How do they come to this? We know that 56 over 8 gives us a 7. Now, if they say 0.5, that means we are adding a 4 here. So meaning they got this 60, they divided by 8, not so. They divided by 8. Let's check and see. 60 divided by 8. 7.5, good. Then that means it is the same thing we are supposed to do here. Divide through by 8. This one will give us a 7. This is the one you're seeing here, 7 grams of carbon monoxide. You see? That means this way I will also do the same. Divide by 8. Even here, divide by what? By 8. So they said that, what do we have? What is the total volume of the product gases? Total volume. So total volume, first of all, this is 1 mole. Then this is 2. So that makes it 3. Okay? So that makes it 3. So we have 3 moles, and 1 mole of a gas occupies what? 1 mole of a gas occupies 24 liters under room conditions, right? So we shall multiply by 24. Okay, that is our gas which they are going to produce, the volume of the gas they are going to produce, decimeters cubed. Now we shall divide this one by 8 because we have been dividing everything this way by 8. So dividing this one by 8, you have 24 divided by 8, you get 3. Then 3 times 3, that one gives us 9 decimeters what? Cubed, which is C here. Question 24. 3 statements about ammonia molecules and ammonium ions are given. In an aqueous solution, ammonia molecules form coordinate bonds with hydroxide ions. Okay, no, that is not actually the case, because ammonia molecules, we see the lone pair of electrons on the nitrogen. This one is supposed to be donated to we call it something that doesn't have the electrons, that is electron deficient. Isn't that an electrophile? An electrophile can be positively charged, you see. It needs electrons because it lost them. But now the OH here, for it is a nucleophile. So these two are actually nucleophiles, so they cannot react. You see that? So it's not a coordinate bond in there. So that is off. So wherever there is one, I just cross it here, here, and here. That means the answer is C actually. But let's check 2 and 3, which are in C. Option 2, they are saying ammonium ions are Blonstad-Lowry acids. Yes, that is true, because if you have ammonium ions, this is NH4 plus. This one can react with, we can react this one, let's say, with water. Okay, what do you get? You can get, let me actually use, if you get any ammonium salt and you react it with a base, a strong alkali like sodium hydroxide, ammonia is going to be driven off. So you are going to get ammonia here, then plus, what else here? We are going to have water, not so? Leave the sodium ions there, then plus the water. Because if I had, like, let's say, a chloride here, then we would have formed sodium what? Chloride. You see that? So that is what happens. So in this case, this ammonium ion has lost the what? A proton to give us this. So that is okay. Then we go to this one here. The nitrogen hydrogen bond angle is larger in the ammonium ion than in the ammonia molecule. In the ammonium ion, we have here tetrahedral. So remember, the lone pair of electrons here is donated to the hydrogen ion. So we have something like this in ammonia. So the electrons are donated to the proton here. Remember, hydrogen has lost its electron, so it's only remaining with a proton. That is why hydrogen ions, we call them what? Protons. And then here we have hydrogen, and hydrogen. So because this is tetrahedral, the angle is 109.5 degrees using electron pair repulsion what? Theory. But then in ammonia, because of the lone pair here, then there is repulsion here between these three here. So we are going to have this angle. The lone pair, bond pair repulsion is stronger than bond pair. Okay, so in that sense, this angle here is going to reduce. Okay, and it becomes something like 107. So this angle here is bigger than this one. So this is true. That is why the answer is what? C, which is 2 and 3. Question 25. Ethene reacts with steam in the presence of sulfuric acid to give us an alcohol. Which type of reaction is this one? This one is an addition reaction. You get 2 or more reactants, okay, and then they react to give you one product. As simple as that. Question 26. Compound Z has the molecular formula, this one here. So if there are two oxygens, it can be a carboxylic acid or it can be an ester. Are we there? It can be a diol, an alcohol with two OHs, right? Then compound Z reacts with propan 1O. Now an alcohol cannot react with an alcohol, so it is not a diol. You get it? Then it is also not, so they are saying compound Z reacts with propan 1O in presence of sulfuric acid. An ester cannot react with an alcohol, so this one is not an ester. You see that? This one has to be a carboxylic acid, because a carboxylic acid is the one that reacts with an alcohol in presence of sulfuric acid to give you an ester. So the diagram shows the skeletal formulae of three compounds S, T, and U. What are the possible skeletal formulae of the products of the reaction between the compound Z, which is a carboxylic acid, and propan 1O? Now, if I have Z, which is this one, we have said that one is a what? Carboxylic acid, butanoic acid. So we shall have CH3, CH2, CH2, C, then OOH. So the carboxylic acid in such a reaction loses the OH, and then the alcohol loses the what? The hydrogen. Okay, so we are going to have CH2, propan 1O, okay? CH2, CH2, and CH3 here. So this one loses the hydrogen, the alcohol, and then the carboxylic acid loses the what? The OH, and then water is given off. So that's why we call it a condensation what? Reaction. So we have CH3, CH2, CH2, then C, then O, this O here, and then this O here now. Then we add on CH2, CH2, CH3. This is propyl butanoate as an ester. Now we look through here. Let us begin with this S here. So this O here, where it is, the alkyl group that is connected to it, then it comes from the alcohol. So this is CH3, CH2, CH2, OH. Yes, that would be the propanol. Then this is COO. Then this is CH2, CH3. These are three carbons, yet we need how many carbons? They have to be four for butanoic acid. Okay, so that means S is off. Since S is off, then wherever there is S, we cancel it. There is this one and there is this one. Let's go to T. This is CH3, CH2, CH2, OH, that is coming from the propanol, yes. Then this is C, then OO. Then there is CH2, CH2, CH3. It is the exact thing here. CH3, CH2, CH2, COO. CH3, CH2, CH2, COO. You see that? That is the butanoate. And then the alcohol here. So that means T is okay. Okay? This one is okay. So wherever there is T, then I put a tick. So it has to be here and also here. But since I put a cross here, then that means that A is off. Then this is the answer here, D. But let's check U to prove that it is also wrong here as option B. So this is CH3, CH2, CH2, CH2. Now that means the alcohol here is butan 1O. Do you see that? This is CH2, CH2, CH3. This is actually butyl butanoate. You see that? So that means this one is wrong. Question 27. Geranio and Nero are isomers of each other. Okay, the structures are given. Which type of isomerism is shown here? The fact that we are having a double bond, okay, we think of stereoisomerism, and in particular, we look at geometrical isomerism, the cis and trans. Now look at the two carbons in the double bond. Let's begin with this one here. So this carbon here has two groups that are the same. That means this one cannot have the geometrical isomerism. Okay. Then when we come to this one here, this carbon has gotten this group which is different from the whole of this. Then also this carbon has gotten this group that is different from this. That means this one can have the geometrical. So there is cis and trans. Usually people are used to the cis to be that maybe this is the hydrogen, then this other side, you can have the hydrogen here. Then for trans, hydrogen can be this side, okay? And then this one is this other side. The groups don't have to be identical. Okay, what I mean that you must have a hydrogen here and also here, or this is a methyl here, then you must also have a methyl this side. No. Now for this case, the cis is going to be the big groups are on one side. You see that? Hey, then, or maybe when this one is this other side. So where you have this big group and also the CH2OH this way. And then when hydrogen goes this side, I mean when hydrogen is here and this big group is also this other side, then this one is going to be trans. You get it? Then when we come to this one here, they just substitute them. You can see they switch to them. So I can take this one to be my let's say trans. The big groups are on opposite sides of this one pipeline. So but here the two big groups are on the same side, then I can take that as cis. So that means this is geometrical isomerism. Question 28. Which compound has the greatest number of stereoisomers? So for stereoisomers, we look at optical and geometrical. So for optical isomerism, we have to look for the chiral center, that carbon which is connected to 4 different groups. And then for geometrical, just like I've said in the previous number, we have to look at the 2 carbon atoms in the double bond. Do they have their groups that are attached to them different? Okay, is this one different from this? Or is this one here different from this? But again, if this one has 2 groups that are different from each other, but then this one has identical, then the isomerism fails there. Okay. All right. Now let's go. This is 2-methyl hex 2-ene. So this is 1, 2, 3, 4, 5, 6. That is hex. Then 2. That means the double bond is on the second one here. Then 2-methyl. So put the CH3 here. That means this one will have a CH3 there. Then a hydrogen here. Then a CH2, a CH2, and a CH3. So no carbon here is connected to 4 different groups, no chiral center, so no optical isomerism. This carbon here has gotten the 2 methyl groups attached to it. That means it cannot have what? Cis and trans or geometrical isomerism. So we can only take what? 1 isomer from there. You see that? Then let's go to this one here. By the way, this one has 2 groups attached to it. It has the hydrogen and then this other group here. They are different, but this one has identical. That is why the cis-trans isomerism fails. Okay. Then when we go to this one here, we just shift this CH3 to where? To the third one here. Okay. So I'll just get this one here, then duplicate it, and then I take this one here to this carbon here, then take away this hydrogen, bring it down here. So like that. So after doing that, then this one I can bring it here. Now you can see here that this group is different from this. Yes. Then also this group is different from this. So this one can have the cis trans, okay? So that means here we have 2. Then let's go to this one here. 4-methyl X2N. I'll just get this one, duplicate it, okay? Then take away the methyl from here, put it on this one here. Because we are reorganizing this, I'm going to take away this, then put 1 hydrogen. Remember, I've taken away 1 hydrogen from here, then it has to go to this carbon here, okay? So meaning I'll get a hydrogen, and then I'll put it here, and then take away this one here. You see? Now, maybe to make this one much more presentable and well displayed, let me first take it down here, then I put the hydrogen here. So you can see that this group is different from this, different from the whole of this, different from the whole of this. So this one here, this carbon, is therefore a chiral center. So it will have the enantiomers, or the 2 optical isomers, right? But also here, this carbon here that is in this double bond has gotten this group and also this other group. They are different. Are we there? Just as this carbon here is connected to the methyl and then the hydrogen, which are also different. So that means we are going to have cis trans here, and then we are also going to have optical isomerism here. You see? So altogether, this one is going to give us how many? It is going to give us 4. The 4 are going to be like how you can have the cis trans. Maybe here I'm going to take 1 and 2, okay? Optical isomer 1, and then there is optical isomer what? 2. That means I can have here cis, then together with optical isomer 1. Then again I can have cis, and then optical isomer what? 2. Do you see that? Then again trans, I can have trans here, and then optical isomer 1 here. Then we can also have trans, and then optical isomer what? 2. So this makes it 4. You get it? Now let's continue. Then this one here, we are going to get this one here, then duplicate it. So we move the methyl from here, we put it onto this one here, because this is 1, 2, 3, 4, then 5. Let's say 5-methyl. Okay. Then what else? Of course, a hydrogen has to get away from here. Okay. And then we put it here. So you can see that is everything all right here? You can see here that I must be having something wrong here. This is 1, 2, 3, 4, 5, 6. Yeah, 1 carbon I think was supposed to be off. Pardon me here. This carbon here is supposed to be off. And also here, I've been doing the same mistake. Kindly pardon me. So let me put everything in order. So that is what we are having. 1, 2, 3, 4, 5, 6. Okay. Even here. So let me put this one there. And also here. This one would have been a chiral center, but it has a methyl and a methyl. Are we there? So it can't. And then these 2 carbons that are in the double bond, they have 2 different groups. So this one is different from that, and also this one is different from this. So that means this one is going to have the cis trans. Okay, cis trans, and these ones will be 2. So that means the one with the greatest number is going to be which one? This C here, the 4-methyl. We have seen there 4 there. Question 29. Vitamin A contains retinol. This is retinol. And they are saying under appropriate conditions, acidified potassium permanganate can be used to break the carbon-to-carbon double bonds. That means this one has to be hot, acidified, and concentrated, okay, and conc. But if it is cold, okay, cold, acidified, and dilute, then we shall get OHs here, diOs, wherever there is a double bond, okay? So to break this double bond completely, and then oxidation takes place, we must have hot and concentrated. So these ones have to be off, right? And then final products. So since here we have the CH, then also here a CH. Here you have just a carbon and a carbon. Then here a carbon, because the carbon must have 4 bonds, right? Then even here there is a hydrogen, because you have 1, then 2, 3, and then 4 bonds, right? The hydrogens that are directly connected to the carbon are always hidden with the carbon in the skeletal formulae, okay? So even here we have carbon and a hydrogen, then carbon here with a hydrogen. So when we break, we shall break this one here, and then we oxidize. So here you will get first an aldehyde, but then later a carboxylic acid. Then here you will get a ketone, because you have a group here and then a group here, okay? So you'll get a ketone. So I'm seeing carboxylic acids, okay? Then I also see what? Ketones, R, and maybe R here. So ketones, carboxylic acid here, and even this one actually will be oxidized to carboxylic acid. Then here a ketone, here carboxylic acid, and then here also carboxylic acid, ketone, carboxylic acid, then here a ketone, and then here a ketone. So we only see carboxylic acids and what? And ketones. So the answer has to be this one here. So we have our answer as D. Question 30. The structure of limonene is shown. This is the one here. Then they say, what are the number of moles of carbon dioxide and water produced when a sample of limonene is completely combusted? So let us first see the molecular formula. So here there is a carbon, there is a hydrogen here. There's a carbon, then 2 hydrogens. Carbon here, there's a hydrogen here. Then a carbon here, CH3. Then here we have CH2 also. C, then also H2, C here, then C, H3 here, then C, then H2. So what are we going to have here? Carbons, how many are they? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10 carbons. So if we have 10 carbons here, how about hydrogens? These are 2, then 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, we have 16 hydrogens, and we don't have any other. Okay, then plus oxygen, this one should give us, for complete combustion, we get carbon dioxide and what? And water. Then to balance this, since these are 10 carbons, I'll put 10 here. Hydrogens are 16, I'll put 8 here, such that I make this one what? 16. And then oxygen, this is 8 plus 10, plus 20, that is 28, not so? That means here I will put 14, because 14 times 2 gives you what? 28. Now, they are saying number of moles of carbon dioxide. Now, for us, we are seeing how many? 10. But here we don't see any 10. But there is a what? A 5. Okay? A 5 goes into 10. So that means if we get a half of this, if we multiply all through by a half a mole, because this is, you are combusting 1 mole, okay, which gives you 10 moles of carbon dioxide and 8 moles of water. Now if you combust a half a mole, this one is going to be, what will be needed here is a 7. In other words, I'm multiplying all through by half. Okay, so this one will be 5, and then this one will be what? 4. So 5 moles of carbon dioxide and 4 moles of water. So that means our answer is what? B. As simple as that. So when they were saying a sample of limonene, it doesn't necessarily mean that we were burning 1 mole. Okay, it can be half or any other amount.